There is another type of NP-complete problems in which we are given again a set of objects, but somehow we need to select a subset of them that gives us a certain total weight or value. We will look at the knapsack problem that you have seen before, but actually before we prove that the knapsack problem is NP-complete, we will prove that a simpler version called subset sum is NP-complete. And then I will also show you how you can use this problem to prove that a scheduling problem is NP-complete. So here is the subset sum problem. It's very simple. We're given n numbers. Think of them as natural numbers or positive integers basically. And we're given another positive integer w. We're asking the question, is there a subset among these n numbers that when we add that subset we get exactly w, no more or no less. So imagine that we have these numbers here and I give you the number 3754. Can you find a subset of these numbers that when added gives 3754? This also shows, by the way, that the problem is clearly in NP because it's very simple if somebody gives you a candidate solution to check indeed that the sum of those numbers gives you W. So is this a hard problem or is it an easy problem? We will prove that it is actually a hard problem by doing a reduction from 3SAT. Now, if you look at your textbook, the reduction is different. It's not from 3SAT, it is from the 3D matching problem. But given that we didn't really go through the proof that the 3D matching problem is NP-complete, I prefer to give you another proof that is based on the 3SAT problem. Now, let's look at the reduction from 3SAT to subset sum. 3SAT has to do with Boolean expressions, subset sum has to do with numbers. So the reduction somehow has to be able to take us from expressions of Boolean variables to numbers that we can add and get a certain sum. Let's see how we can do that. Suppose that the expression of 3SAT that we start with has n variables and k clauses. Okay, so in this example, for instance, we have 3 variables, x, y, and z, and we have 3 clauses, right? So as we will see, we will construct numbers that have n plus k digits. We have n digits for the variables, x, y, z, the first 3 columns, and k digits for the clauses. We have these 3 columns for the clauses. How many numbers do we create? As we will see, we will create 2 n numbers that correspond to the n variables, both in the positive form and in the complementary form of each variable. And we will also construct 2 times k numbers. Now, how do we actually construct these numbers? Let's pick, for instance, the first one that corresponds to the variable x. The variable x, as you can see, appears only in clause C2. So the first 3 digits here are 100 because, of course, this refers to the variable x. This literal x refers to the variable x. And there is another one here because this x appears only in clause 2. Let's look at the second number, this literal, which is the complement of x. As you can see, it appears in clauses 1 and 3, right? So again, the first 3 digits are 100 because this literal, it relates to the variable x. But these digits are 101 because this literal x bar appears only in clauses 1 and 3, okay? So which are the 2 first numbers we constructed? The first one is 100,010, in other words, 100,010. And the second number is 100101, in other words 100,101. Now, in the same way, I will not repeat the whole story, you can get this number, this number, this number, and this number for the variables y and z. The numbers that we construct, these last 2k numbers, they have a very clear pattern, as you can see. The first three digits are all zeros. And then in the last three digits, we have 1, 2, 1, 2, and 1, 2. So the numbers are 100, 200, 10, 20, and 1 and 2, right? The target number of the subset sum problem, this uppercase W, will always be 1, 1, 1 for the first three digits, 4, 4, 4. Now, all of this may seem very surprising and perhaps weird, but let's see what is the rationale behind constructing the numbers in this particular way. The first point is that in a three-set expression that is satisfied, each variable has to be either true or false. It cannot be both, right? So it will be that we either select this number, the number that corresponds to x, or this number, the number that corresponds to x bar. We are forcing ourselves to select one and only one of these two numbers because the sum, this uppercase W that we will get, has to have 1 in the first digit. So if we would not select this number and we would not select this number either, then we would not be getting 1 in the first digit. If we would select both of these numbers, then we would be getting 2 in this digit. By having this digit being equal to 1, we're forcing ourselves to select either this number or this number, right? And that ensures that x will be either true or false. It cannot be undefined and it cannot be both true and false. And of course the same, as you can see, happens for y and for z, right? By having this digit being 1 and this digit being 1. Now, what are we trying to do here with this force, y4? Basically, we want to make sure that if the expression is satisfiable, right, this means that each clause is satisfiable. This means that for every clause, we can find at least one literal that is true. So, looking at the clause columns now, a clause, as you know, in 3-SAT always involves three literals. Let's see, for example, C1, it involves the literal x bar, y, and z, right? It has to be that one of these three literals at least is selected. In other words, one of these three numbers is actually selected. And so looking at the digit that corresponds to C1, which is this digit right here, if we end up selecting all of these three literals, if all of them are true, then we will have 1 plus 1 plus 1, 3. We can make sure that the sum is 4 by selecting this one digit, which is a single one. In that case, we have 1 plus 1 plus 1 plus 1 is 4. What would happen if we had selected not three of these numbers, but say, for instance, only two of these numbers, meaning that only two of these literals are true? Then again, we can force the sum to be equal to 4. How? We will have 1 plus 1 plus, we have the number 2 here. So again, we can get a sum of 4. If we have selected, if only one of these literals is true, let's say, for instance, this one, the x bar, right? And so we have selected this number. Again, we can get a sum of 4. How? We have 1 plus 1 plus 2, that gives us again a sum of 4. But what cannot happen is that if we haven't selected any of these numbers, if none of these three literals, in other words, is true, then we cannot get a sum of 4, because the only thing that we would, the only numbers that we would select here would be 100 and 200. Well, that gives us in this column a sum of 3, not a sum of 4. So by creating these numbers here and by selecting an appropriate subset of them, we can always make sure that in a satisfiable expression, every clause is satisfied, and so we can always pick numbers that correspond to the literals that are true in each clause. Now that we have seen that the subset sum problem is NP-complete, let's see how we can use that fact to show that the knapsack problem is NP-complete. Now the knapsack problem is a problem that we saw back when we were discussing dynamic programming. Let me remind you, we have again n objects and we're given some knapsack that has a capacity of w, that's a positive integer. And each of these objects has basically two things, two properties. One is the value, vi, and the other is the weight. Now we are trying to maximize the value that we will get from the knapsack, subject to the constraint that we cannot exceed its capacity. So if I give you this set of objects with values and weights, and I say that the capacity is 11, it turns out actually that if you choose the items 3 and 4, you satisfy the weight because it will be 11, and the value is actually maximized. You get a value of 40, you cannot beat that. This is the dynamic programming solution that we came up with a long time ago. I will not repeat the dynamic programming algorithm here. I just want to remind you a couple of things. The running time of the algorithm, as you remember, was big O and the number of objects times W. So when you look at this, is it a polynomial time algorithm with respect to W? With respect to W, yes, but in order for the algorithm to be really polynomial time, not pseudo-polynomial time, it should be a polynomial time function of the number of bits that we need in order to represent this number W. So let's now prove that the knapsack problem is NP-complete using a reduction from subset sum, because subset sum sounds so similar to knapsack. First, we need to transform the knapsack problem into a decision problem. So the usual trick, as you know by now, is that we can change an optimization problem into a decision problem by introducing a certain variable. So in the knapsack problem, the original one, we were given a finite set X, and each object had a weight and a value, and we had a limit for the knapsack capacity. We were trying to maximize the sum of the selected object's value. Here in the decision problem, we are also given a target value, and we are asking the question, is there a certain subset of these objects that, let's call it S, that will give us a total weight that is less than the capacity of the knapsack, less or equal, and that has value that is greater or equal than the target value, right? So this is a decision problem because the answer is, of course, yes or no. The subset sum problem was already stated as a decision problem. Namely, we're given a finite set X again. The objects have a value, let's call it UI. These are the numbers basically. And we're given a target number uppercase U. We're asking the question, is there a subset S of these numbers that when added gives us exactly the target number uppercase U, right? So this is the decision version of the two problems. we want to do the reduction from subset sum to knapsack, which means that for any instance of the subset sum problem, let's say we have these n numbers, u1 through un, and we are given this target number u, we are asking first of all to construct a specific instance of the knapsack problem such that the subset sum instance has an answer yes if and only if the knapsack instance has an answer yes. The construction in this case is really simple. We don't need a gadget or anything like that. Specifically, the objects can be the same n objects that we have in the subset sum problem. The value and the weight, they are equal in this case, equal to u I, right, for every object I. And our target value is the same with the capacity of the knapsack W, which is also the same with this target sum, right? So we are constructing the knapsack instance as follows. We want to select a subset of these n numbers, right? So that their total sum is less or equal than the uppercase u. This is the capacity constraint. And at the same time, the sum of these numbers is greater or equal again than u. That is the target value. Now, of course, because we want these inequalities, both of them to be true in the knapsack problem, the only way they can be true is if the summation of these ui's is actually equal to this uppercase u, which is basically what would satisfy the subset sum problem. So if the subset sum problem has a solution, then this knapsack problem, of course, will also have a solution because both of these inequalities will be satisfied. And in the opposite direction, if the knapsack problem has a solution, then we can use this same subset S that satisfies these inequalities, both of these inequalities, to satisfy this equality, which basically would give us a solution for the subset sum problem. Let's close this lesson with a scheduling problem that, as we will see, has some relation with a subset sum problem. You have seen scheduling problems before in this course. When we were talking about greedy algorithms, we saw a scheduling problem in which the jobs had a certain processing time and a deadline, but still we were able to schedule them using a polynomial time algorithm. Here I will show you a harder scheduling problem in which every job has a processing time, how long it will take, Ti, a release time, that means the time at which the job arrives, right? You cannot start working on it before the release time, and it also has a deadline. You cannot work on it after the deadline. And so the question is, if you get these n jobs, is there a way to schedule them on a single machine, a single resource, so that every job I can be processed between the time it is released and its deadline without interrupting it? So it's not okay to start working on a job and then interrupt it to execute another job and then go back to the previous job. For example, if we have only two jobs, let's say 1 and 2, suppose that for the first job we have these characteristics, and for the second job we have these. You can see that if you start working on job 1 and it will take you until time 3, you can meet its deadline, but then you will miss the deadline of the second job. And on the other hand, if you start working with job number 2, you will meet its deadline, but then you will not have time to work on job number 1 before its deadline. So in this case, this is an instance of the problem where there is no solution. Let's now prove that this scheduling problem is NP-complete. We will rely on the subset sum problem. First of all, the scheduling problem is clearly in the class NP, because if you give me a schedule, I can go through each job and check that it meets its deadline. I can do that in polynomial time. How does the reduction work? We start, of course, with any instance of the subset sum problem. Let's say you give me these n numbers, wi, and the target sum is uppercase W. How do I construct an instance of the scheduling problem so that it is solvable if and only if the corresponding instance here of the subset sum problem is solvable? The way that we will do it is by having these n jobs having a processing time that is equal to the corresponding value of W. So the I job has a processing time which is Wi. The release time of all of the job is 0, right? We simplify that way. And the deadline of all of the jobs is the same. What is the deadline? Let's say that uppercase S is the summation of all of these WIs, right, for the n numbers. In other words, in the scheduling problem, this S, uppercase S, is the summation of the total processing time of all the jobs, right? So we set the deadline of all of the jobs to be 1 plus S, right? What does this mean? That if we only had to process these n jobs, the order of the schedule wouldn't matter because we would always be able to complete all of them before the deadline. Now, what makes the construction interesting is that we are adding one more job, a special job. Let's call it job 0. That job has a processing time of only 1 unit, and we release it at this very special time W, which is the target sum in the subset sum problem. And we also set the deadline for that special job to be W plus 1. So this job basically has to be executed at the time between W and W plus 1 because it is not available before W and it will miss its deadline after W plus 1. Now that we have the constraint of this special job, we see the connection between the subset sum problem and the scheduling problem. If the subset sum problem has a solution, it means that there is a subset of these numbers that when we add them together gives us W. If that is the case, then we can schedule the corresponding subset of jobs in this interval, and the total processing time that they will take will be exactly equal to W. The rest of the jobs then would be executed in this time interval, and again they would not miss their deadline because the total processing time of those jobs will be S minus W. Right? So this shows that if the subset sum problem has a solution, the scheduling problem also has a solution. In the reverse way, if the scheduling problem has a solution, then we can find out basically which jobs were executed in this interval and choose the corresponding numbers as the solution of the subset sum problem. Notice that because the deadline of the n jobs is set to 1 plus s, we cannot have any idle time in the schedule. So in this time period here between 0 and W, there cannot really be any gaps. This is necessary so that we can show that the summation of these WIs for the jobs that are in this time interval is exactly equal to W.